everyone. Thanks for joining me on the Slice of Healthcare podcast. I'm your host, Jared Taylor. Joining me today is Dr. Jonathan Stein, the Chief Science Officer at Tesis, right? I'm saying this right? Tesis Biosciences.
You got it.
Love it. Awesome. I'm hyped to have you here today. Uh, let's kick things off. Tell us about your background.
Well, it's great to be here today, and thank you for having me. My name is Dr. Jonathan Stein. I'm the Chief Science Officer and Medical Director for Tesis Biosciences. My background, molecular genetics of cancer, no big whoop. Did paternity testing, forensic testing, heredity testing. I've been CSO for a couple places, consulting lab director for many, many more of them. During the sort of big COVID explosion, gosh, I was running 5 labs at the same time. So that was fun and interesting. Um, nobody gets into being a lab director for the white knuckled adrenaline. But there we were doing, 7 days a week, going to double and triple shifts in some of the laboratories. It was a really wild time. So that's kind of where I'm coming from. Got my undergrad at UC Santa Cruz, go fighting banana slugs, and came out to Texas to get my degree working in molecular pathology at MD Anderson Cancer Center. So that's the kind of short end of the story.
Oh, very cool. I knew someone at MD Anderson for a while. I mean, I know it's a big place. You might I know Dr. Gary Bridges. Um, yeah, he
Big
used to.
institution.
Yeah, it's a huge place. So
Mhm.
yeah, really cool. Um, fighting banana slugs? Is that what you called it?
Yeah, Santa Cruz has their mascot is the banana slug. It's this
Oh
kind of
my.
long, kind of gross looking yellow thing. We're not very sports minded.
Okay. Um, okay. All right. I'm trying to picture it right now. I'd love for you to give us an overview of Tesis Biosciences now, and maybe talk us through the biggest challenges that you're helping to address. You're helping your customers address today.
Sure. Tesis Biosciences is a next generation sequencing lab. And what that means is we develop gene specific panels for specific diseases. We sequence all the genes that have been identified that are associated with a disease state. And then we kind of winnow those large lists of diseases, of gene associated diseases, to ones that are clinically actionable. What does this tell you about your risk? What does it tell you about the likelihood of getting a disease severity in some cases? And in some cases, how best that disease can be treated or avoided. So this, there's 20,000 genes in the human gene. There's a lot of genes out there. There's a lot of research using sort of statistical methods to identify genes associated with this. And you can generate a lot of information with next generation sequencing, but it needs to be actionable. Like, it needs to be useful. Like, imagine how busy a doctor is every day seeing all those patients. They need to know what they need to know, right? And so, as fun as it is to be a geneticist and to geek out and to look at constellations of data and weak genetic interactions and try to figure out what all that means, how can we help the patient? How can we help the clinician help the patient? So that is our focus. I cast this enormous net and I geek out like you wouldn't believe, because I love, love, love genetic research. And then I boil that down to what's going to be useful. And so that is one of the things that Tesis is really focused on, is clinical relevance, clinical actionability, right? You can imagine making these comprehensive gene panels, hundreds and hundreds of genes. One of them's only been seen in 2 families in Pennsylvania, and they know they have it, right? How helpful is it to give that information to random clinician for random patient? It's just noise. It's just more and more noise. So in a very distracted world, we try to help focus that information, again, with an eye towards clinical utility, clinical actionability.
Can you talk us through why understanding genomics is so important for the future of health?
Sure. Again, as a mad scientist, I'd say it's because it's awesome. But um, let's talk about so there's a thing called pharmacogenomics. This is a beautiful example because it really highlights a lot of what the value is of this testing. So we all take almost everybody takes some medications. Some people take lots of medications. And it turns out for any given medication, for any given patient, some people are going to metabolize that drug really quickly, and some of them are going to metabolize it very slowly. So in one case, it leaves their system very quickly because they're a fast metabolizer, and in some cases, it can sort of accumulate in their system because they metabolize it very slowly. So that means on an average dose, some people are getting way more than they need because it's floating around their system, accumulating. You say you're taking 2 or 3 pills a day, you're not really flushing them out of your system, so it's adding up. Or they're not getting enough because they're very, very quickly getting it out of their system and breaking it down. So what's the bottom line on that? The bottom line on that is women who get pregnant on birth control, right? Because their body breaks it down faster than it can accumulate enough to impact their sort of hormonal balance, which is the whole kind of actionability of the birth control. And for people who are slow metabolizers, probably the best well-known example of this is so if you take, what is it, codeine 3, right? The intermediate metabolite of that is morphine. And so you can have cases where a mom who got a C-section, and so she's taking Tylenol 3 as a painkiller, her infant can get opiate poisoning because she has accumulated morphine. They're both super slow metabolizers. So this intermediate breakdown product of the codeine is morphine, and that's going through the mother's milk and getting into the baby and problems, right? Turns out being a fast metabolizer or a slow metabolizer is common. Like 20% of people total will be on one end or the other end of that. So you have these really common, like it's not a super rare thing at all. This really common genetic variant that everybody has for one medication or another, right? And it's incredibly helpful to know. We're looking at it for one of the big avenues for this is mental health. If somebody shows up and they need to be prescribed, they have extreme anxiety or suicidal ideation or psychosis, right? And they need to be on an antipsychotic or an antidepressant or an anti-anxiety. Um, Almost everybody who knows someone who's been through that process, they get prescribed a drug and they get told, okay, well, come back in, 10 weeks, 2 months, 8 to 10 weeks, and let me know if you're feeling less psychotic. Let me know if you're feeling less suicidally depressed. Let me know if you're feeling less so anxious you can't even function. Let's see if it works. And if it doesn't work, we'll try something else. Genetic testing can tell you which ones are most likely to work for you, which ones are less likely to work for you, whether the dosage is going to be whether you're a slow metabolizer, so you're going to get lots of those negative side effects. You don't need to take as much of the dosage, or if you're a fast metabolizer and it's never going to work for you because your body breaks it down. Maybe you need something different, maybe you need a higher dose. Giving people that heads up is a huge quality of life difference. So that is that's today. Like you can go get those tests today. That's not the future of this, which I'll be happy to rant about.
Yeah, no, I'd love to get your take also on the future
Yeah,
a
but
piece of it as well.
it's a big deal, right? So what that looks like in my mind. So okay, the cost of sequencing is going down, 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 right? And the first one cost millions and millions and 20 years to sequence somebody. Now you can get it done for about $1,000 if let them use your sequence data to do what sort of further research analysis, right? Um, and that's going to keep going down. It'll probably half again within the next 5, 10 years, right? So there becomes a point where the most valuable thing to do is just sequence people, find out what their hotspots are for what their what's the word I'm looking for, um, what can be easily prevented, like what they're vulnerable to. Here's the pieces you probably shouldn't go around, and then all of their medication gets sort of front loaded. They don't take this, they do take this. If they ever, get on anti-diabetics, or they ever get on they ever get on psychiatric drugs, or if they ever get on cardiovascular drugs, here's the route that's going to be most successful. Like that's all where it's going, and it's going to generate a tremendous amount of what's called bioinformatic data, right? You sequence someone, that's a lot of information. It's a lot of genetic information to try to parse out what's useful and what isn't. And so the same thing we'll be doing. What is useful? What is useful to know? I did a 23andMe, loved it, told me my eye color. I already know my eye color, right? It's lovely, but also, right? Um, you know, again, that's recreational. People who go into a clinical setting, they need to know what is most important, what's most relevant, what's most actionable. So that's only going to keep going. I mean, the internet's kind of like that. Within this like fire hose of data, you want to know what you want to know. Like what can you use?
Let's talk a little bit about why understanding genetics is key to highlighting vulnerabilities in infectious diseases. Can you talk about that?
Yeah, sure. So, um, where to begin with that? So what happens is you look at the way this is done is they do large scale research studies and they look at different outcomes for a given disease, right? And they do what's called a genome-wide association study, where again they either look at like enormous panels of genes or they just bulk sequence people, depending on sort of the level of granularity they're going for. And from that, you can identify what subsets of people are most likely to, like for COVID, for example, you can identify the people who are most likely to be hospitalized, most likely to have severe outcomes, most likely to be asymptomatic, right? So this gives you like sort of two interesting things to follow up on, right? One, you can find out what your risk is, right? And again, this is all sort of statistic, right? So you can know like, oh, okay, I'm in the lowest risk group. I'm not saying that that means you can go, hit the raves, right? But it does mean that, if you are at the highest risk, maybe you really shouldn't, right? Maybe you are the ones who really need to minimize your exposure because you're at the highest risk, right? So that piece is helpful. And then the other part that's kind of interesting is from there, when you look at these variants, well, what's the underlying mechanism of action, right? When they originally looked at, what do you call it? 1,000 years ago, when they were looking at HIV transmission, they found some sub-Saharan African prostitutes who didn't get it. They couldn't get it. And from that, they identified the particular pathway by which HIV gets into your immune system cells, their receptor, the sort of lock to the key that HIV was using to get in, was shaped differently. Key couldn't get in, they were immune, right? And from that, you could try to develop different pharmaceutical interventions. And again, you can identify risk and you can also identify treatments, hopefully.
Now, what are some of the things we can learn? The genetics field as a whole can learn from the COVID-19 pandemic, and I guess how do we apply that in the migration of future pandemics?
Oh, interesting. So, some things. So, okay, a little bit of background. So, I worked briefly in a level 5 biohazard facility at MD Anderson. I got to wear the spacesuit, super fun. They're very uncomfortable, but it's really neat. And did molecular epidemiology, did some public health training. So, got an A in virology, so that's fun. So I do have a bit of a background in this. So, I'll be riffing, but I know somewhat whereof I speak. And there are a couple things that they got right. Our sequence capabilities are so good that we could do that very quickly. And our ability to identify genetic variants, that's all bulk sequencing power, right? So we could identify the infectious agent quickly. And we could look for variants in genetics very quickly. So that's great. But that lags far behind treatment, right? Diagnostics is always just galloping ahead, right? So maybe some variants will give you clues to treatment, but you still have to develop the treatments. You have to show safety and efficacy. There's a um, there's a regulatory mountain to climb, right? And that part is hard. And honestly, I don't see that part because it's sort of independent of the science piece, right? We are really good at identifying genetic variants. We are really good at developing diagnostic assays. We didn't scale them very well, very quickly, right? Um, that took that lagged a bit, So we had really advanced laboratories doing very high level work of excellent quality, and that filtered to a retail level. right? Not as well as it could have. Will that change in the future? Only if the underlying barriers change.
I have Dr. Stein, I have two more questions for you as we wrap this up, and really appreciate all of your. I appreciate your energy too. You're going to be like probably top five for energy. We've done like 400 of these, and I love the energy that you bring, and I know the audience will too. Uh, next thing I want to go through with you. So where will genomics and genetic testing have the largest impact in preventative care over the next couple of years? Let's say.
Okay, so here's something I've been working on. It's incredibly exciting. Now you got me kind of a little self-conscious about it, but I really love this stuff. I'm a huge fan of genetics. So they recently they sequenced a large consortium of some of the European nation states and some of the larger biorepositories and research biorepositories in the US pooled something like 30,000 patients with assorted mental illnesses. And they sequenced them. And they identified, for example, 28 different separate biochemical pathways that are associated with schizophrenia. Okay, some of the pathways make perfect sense. Biochemical pathway is sort of the process by which your body makes stuff, whether that thing is a protein that cleans stuff up, or if it has some other function. It's just this is the building pathway that your body uses to make functioning uh, things happen in your body. Um, 28 different ones, and some of them made perfect sense. Some of them were like a neural development pathway. So you can imagine, okay, you've got some mutations or some genetic variants in a neural development pathway, and maybe that's not so optimal, and so you're more sensitive to the likelihood of some sort of error that results in schizophrenia. Okay, that makes perfect sense. But some of them were in your immune system. These were variants in your immune system that resulted in, I mean, these patients were diagnosed with schizophrenia, right? And that appears to be the causal mutation for them, right? So what does that mean? Is it an autoimmune thing going on? Is there some sort of infectious thing that's resulting in this? Like what's going on there, right? Those 28 pathways are going to be different, even if sort of on the front end it all gets lumped into a bin called schizophrenia, right? There's 28 different subtypes now, and we know that we can identify them. So some of them are going to benefit from some types of treatment and not others. Some of them are going to benefit from some kinds of prevention and not others, right? And there's going to be this like amazing amount of research that comes out to elucidate these pathways, to kind of clarify what you can do with this information. Like I said before, diagnostics gallops ahead of treatment, right? But it's a really exciting time to look into this.
Yeah, well, it'll be interesting to see how the industry and like your space continues to evolve over time. And I hope everyone in the space is as into what they're doing as you are, because that'll mean great things for the future of genetics and genomics and genetic testing for sure. So I want to thank you, Dr. Stein, for joining me on the podcast here today. Hopefully, we can have you come back again soon, and wish you all the best of
Sure
luck.
thing. It was great talking with you.